Welcome everyone to the DDPS seminar. Before we introduce our invited speaker, let's go over some rules and logistics. First, please mute yourself during the talk. But if you have questions, you can unmute and ask questions, or use chat room to post your questions so that we can address them in Q&A session at the end or during the talk. Second, today's DDPS seminar is open to external audience. Therefore, no classified discussion is allowed, so please watch out. Finally, the talk today will be recorded and uploaded in our YouTube channel. That's about it. Now, let me briefly introduce our speaker today. It is an honor to host Dr. Gabor Sania. Am I pronouncing your last name?
That's approximately, that'll do.
What is the correct one?
Chani.
Chani, okay, Chani. Professor Chani, who is a professor of molecular modeling in the Department of Engineering at the University of Cambridge. He specializes in atomistic simulation and multiscale modeling, integrating quantum mechanics with larger scale systems. His research focuses on applying machine learning techniques to material modeling, particularly in developing interatomic potentials derived from ab initio electronic structure data. Professor Chani also explores statistical challenges in molecular dynamics, such as enhanced sampling algorithms for exploring the configuration space of materials and molecules. He contributes to the Leonard Jones Center, fostering collaborations among atomic scale modeler. Today, Professor Chani will talk about foundation models for materials chemistry. I'm sure we are going to hear a wonderful talk. Now, let me ask informal questions just to get to know him better and to make this seminar somewhat informal. So I just, figured out you have many different hobbies, the climbing, hiking, and sailing, and the coffee making. What is the most enjoyable among? What is the number one things you enjoy among all those?
These depend on, they're on different time scales, right? So
yeah,
make coffee 3 times a day, and that's very important. And I get to sail 3 times a year, which is becoming, I recently started, and that's becoming very important.
Oh, okay.
Best thing to do is to take all my coffee equipment and make it on the boat. So
okay. Let me ask one more question. Because you mentioned sail, what's the farthest the sailing course you took?
I've spent about 5 weeks on the water, sleeping on the boat, but always docking at night. So not open. This is not ocean sailing. This is more coastal sailing.
Wow, that sounds fantastic.
I usually do it in the Adriatic, so
Adriatic,
or Mediterranean seas.
Beautiful. Sounds wonderful. Jealous. Okay, the stage is yours, please.
Thank you very much. Okay, so before I start, I want to emphasize that I'd like people to type questions into the chat as the talk goes on. It's normally when I speak in person, I ask people to jump up and down and interrupt me, but it's harder to do that for you on the Zoom. People don't tend to do that. So, but I think if you type in questions as they occur to you, then that's great. And I can either address them during the talk or we can start with that at the end. Okay, so I'm also conscious that this is a more diverse audience than my typical weekly fortnightly seminar audience. So you're not all molecular modelers. So I've prepared a little bit of a few slides of more extended introduction to this field. So, and what you see here is my group. I guess a couple of years ago, it was our Christmas party. And I also have a very collaborative. We have a lot of international collaborations. Many more than this. I've just listed the people who've been working with me for many years. Okay, so I want to start by talking about materials modeling and how simulating materials and molecules on the computer, of course, is done to support and experiments and theory, and is really a third way of interrogating nature. And there are many length scales on which modeling is done. So you have to pick a length. Often your questions concern a certain length scale, and you have to pick the appropriate modeling framework, modeling regime and technique. So on these axes, I have on the horizontal axis is capability. So atoms, if you talk about the number of atoms, or the time, if you're thinking about forward integrating Newton's law. So the time trajectory of particles. And all the way on the left, you have what I just named the quantum chemistry. So essentially it's the exact solution, or not exact, the numerically approximated solution of the exact real Schrödinger equation, the many-body Schrödinger equation. And that one can do for very few particles and for very few time steps. But essentially, for all intents and purposes, in most of chemistry and most of material science, we can take that to be an exact method. But then, if you want to address higher length scales, more atoms, longer time scales, you have to approximate. And you approximate, for a while, you approximate systematically. So there's density functional theory here, which is kind of a workhorse of certainly materials modeling, to some extent chemistry as well. And one can do 100 atoms and several hundred atoms and picoseconds, many picoseconds if you have bigger computers. But if you're going for longer, then you have to have these much more drastic approximations all the way up to doing experiments, which is not a modeling method. I'll have it. I have it on the slide for a reason. We'll see in a second. On the vertical axis, I have the accuracy, or the errors rather, and these are, I quote them in EVs or in factors of KT, but what you see is that as we approximate, these errors, typical errors, grow rapidly. So how are these methods parametrized? So typically, let's talk about force fields, which is what the rest of the seminar is about. So you have atoms. You don't want to have electrons anymore. You just want to know where the atoms are, how do they move. And force fields have typically been parametrized kind of both from below. So let's make force fields that reproduce some aspects of quantum mechanics, either density functional theory or whatever else, or an even better approximation. Or, of course, we can parameterize them kind of upwards. So basically, we take force fields, we give them parameters that result in, when you simulate with them, properties that you can then compare. And this is why the chemistry laboratory is here. You can compare them to experiment. And many things, many force fields have been built this way. And that's how the world has been operating for the best part of, well, since computers have been invented. And what we're trying to do is something different, is to somehow go in between these expensive quantum mechanical simulations and the very crude and parameterized force fields using machine learning. So we're trying to create a set of methods. We can call them ML force fields. They're going to be slower than the empirical force fields, and they are purely parameterized from below. So that's the key aspect, is that we derive these force fields kind of rigorously from quantum mechanics via fitting to data and converging these approximates. And the idea is, because of this, the idea is that we have no loss of accuracy with respect to whatever quantum mechanics we're parameterizing. So really, we are fitting the atomic energies, potential energy surfaces of atoms as accurately as we desire. But without then having to solve the electrons, we are hoping to gain, and we have gained, factors of millions or billions in evaluation time. And what we give up is not dealing with explicit electrons, but just following where the atoms are moving. So I want to show you a few examples of this and where we are in this endeavor. So, but before that, let me show you what molecular dynamics does when you do it with quantum mechanics. So this is sort of what we are trying to replace in a way. And it's called first principles molecular dynamics, or ab initio molecular dynamics. And this is really a computational microscope for atomic scale processes. So just to give three diverse examples, you can compute phase diagrams. Phase diagrams of materials. It's one of the most fundamental questions that you can ask about a material. Is it solid? Is it liquid? Is it a gas? And if it's a solid, what kind of solid? What's the crystal structure? And density functional theory has been really working extremely well for a wide range of systems, verified to experiment when that's possible, and people are trusting it to go to extreme conditions, like it was done in here by a paper by Julia Gully and her team, many thousands of kelvins, terapascals, which are not accessible in the laboratory. Another example is aqueous solutions of polyatomic ions. So, of course, lots and lots of experiments can access the bulk solution, and you can compute and measure ionization potentials of these ions. And this, you can't see the labels here, but basically it's experiment versus theory, and the FT gives the right answer. So you trust that you're describing the physics correctly, and then you can go in and study details of solvated ions at the atomic level, which you are not able to do experimentally. And the third large area is surface science. So this is a piece of titania, I think a piece of one of these titania surfaces, 110, TiO2, and there's an absorbed molecule on it. And this is the left picture is experiment, but it's under UHV, but you can't really resolve atoms. You see the molecules, they move around, they undergo reactions, they undergo chemisorption, but you don't see the detail. The microscope is just not resolving enough. So on the right-hand side, you see what people do with molecular modeling, with density functional theory. You get the right geometry, you get the correct energy landscape, and that's people have been doing this for decades. So just zooming out a little bit, basically materials properties, stability, both thermal and dynamical, is simulated with this kind of methods. Catalytic reactions, efficiency and selectivity has enjoyed a huge boom from materials modeling. Even complicated things like drug properties, solubility, metabolism. Of course, you're only zooming in to some particular small-scale atomic process that you think is the most relevant or is controlling, for example, at the rate of metabolism for a drug. And of course, there's a huge semiconductor industry, which is able to understand its microscopic materials, the electronics, the detectors, the defects that control the behavior of these devices, all through typically density functional calculations. So the computational cost of these things, and I alluded to this in the first slide, but here's some more detail. So to do a low-level DFT, it's 100 atoms. It's about one compute node, 100 cores, 1 hour to get the single energy of a single structure. And this scales with cubically, typically, in most implementations, it scales cubically with the system size. For insulators, there are linear scaling implementations with very large prefactors. So that's a very niche use. If you want better DFT, then for those who know it, hybrid functionals, then there's a 20 times prefactor typically, and then to the fourth scaling. And the gold standard, which is no longer DFT, but it's a higher level of quantum chemistry, coupled cluster theory, would have an n to the 7th scaling. So this, you can see that one isn't going to make very much progress with these algorithms in terms of the system sizes that are accessible due to this steep scaling. And yet, lots and lots of people use these methods at these accessible system sizes. So what I show here is a few years out of date now, but it's the UK national supercomputer, and it's the usage by code. And just listing the code, the executable names, and you see that there's this thing called VASP, which takes about 35% of all of the UK's academic computer time. And all the green bars are all other codes that essentially do the same thing. So it's molecular dynamics with density functional theory. And if you add them up, then about 40% of the UK's academic supercomputing is doing molecular dynamics with explicit quantum mechanics using DFT. So what happens when you do that? You take atomic positions from somewhere, your initial condition, you solve the Schrödinger equation in this density functional approximation, and you get forces on the nuclei, and then you update the positions using sort of an ODE solver, using Newton's law. And when you go through and just look at the information flow, it is striking that really almost all the numbers that you compute when you do the solution is about electrons and band structure and electron density and orbitals of the electrons, and all of that is kind of thrown away because the only thing that you really keep are the forces. There's a little bit, depending on the algorithms that you use, you can, in the second step, you can use the previous solution to help initialize the next solution. But the numbers that I quoted for how expensive this is kind of already assume that you have warm starts, that you have good initial conditions. So really the idea of deriving an approximation to the potential energy surface, to the forces, is to skip this step altogether and just go from positions to forces using a perhaps very complex but still analytically computable function that you never conjure up the electronic degrees of freedom. And that is what's going to give us the big saving. So really what we need is a energy function, a potential energy function of the potential of the atomic positions. So map from R to the 3n to R. And then the force is just the gradient of that potential. So of course, this idea is not new. And quantum chemists have been doing this for many decades, but for very small molecules. And the typical formalisms, the typical mathematical formalism to write down this function didn't scale very well. They scale exponentially, the way the quantum chemists have been traditionally doing it for decades ago. So the big question is, can we do it not for small molecules, but for materials in general, and for large molecules and molecular assemblies, and escape the sort of exponential scaling? And here's a very small molecule that people have, the kinds of things that people have been doing before, and instead we want to do things like this. We want to take a battery and just run the whole thing, and as if we were doing full quantum mechanics. This is about, I think, here 3,000 atoms. So just to know, we're going to do this in machine learning, and of course AI and machine learning are kind of everywhere in the news these days, and there's hardly a person who hasn't come across that in some form. So I just wanted to share a thought about this. Why am I so excited about using machine learning in this area? And you might say that there's a lot of talk about AI for science here, and this is an example of one of those. I think the computer science companies, the machine learning AI companies, are very excited because it's one of the safe applications of AI. It's not going to kill anyone to do a bit of science directly. So I think that's as opposed to some other uses of AI. So I think that's very safe. But what distinguishes it from traditional uses of AI is that I think traditional ML and AI solves problems that already have solutions, but they want to solve them much, much, much cheaper. And that's as a way of impacting on society, that's huge. But we already know how to drive cars. People drive cars really well. Making a self-driving car would be an amazing feat, in the sense that it would change the economy, it would change the incentives, it would change society in a city. But in terms of what is possible in the world, cars will be driven around. It's not new in that sense. But when we apply ML and AI for science, we are solving problems that are previously not solvable at all. So intractable completely, because they are very, very expensive due to the steep scaling of the examples, these electronic structure methods that I outlined. So if I want to take a drug molecule and ask, is it going to bind to a protein? And I want the answer computed, because it would be very, very expensive to test every single idea for a drug molecule experimentally. Can I do that computationally, we believe the Schrödinger equation certainly describes the system, but with the electronic structure methods, it is absolutely out of the question that you'll be able to run the exact Schrödinger equation on a protein, or even density functional theory on a protein for sufficient length of time that you could answer this question. Or I can run VFT on a material, or an inorganic material for 100 atoms, but I want to study a process that takes 100,000 atoms or 1,000,000 atoms. And so I can't do that with density functional theory. ML allows us to create approximants that with which one can do a simulation that we couldn't do before. And that's the big excitement. So how is this done? I see the first interesting question in the chat, so I'm going to stop. The question is, do these functions have deterministic solutions, or are they approximations? So let me go back to this. So I think you posted this when I was talking about this map from V of R, the energy map from the atomic positions to the forces. And I think the answer is that within a certain framework of electronic structure theory, this map is exact, and one can compute it to arbitrary precision. Now, when I approximate it, I'm going to make errors, and that's not obvious what errors are acceptable, and that depends on what you're going to use them for. Okay? So we are not solving the sort of probabilistic quantum mechanics here. We are not saying I'm going to have a stochastic system because quantum mechanics and measurement is probabilistic. We're going to essentially evolve the system undisturbed. So the stochastic nature of quantum mechanics doesn't really enter into this world that I'm describing. I hope that answered the question. So how is this done? There are a couple of components. So we need we want to derive the energy and the force of an atom. So that's going to depend on its neighborhood. So we're going to need some kind of descriptor for the atomic neighborhoods, and that can and similarity. We can define similarity metrics between different atomic environments. And then we need a regression method. So that could be what I have here. My example is a Gaussian process regression. Or one can use a linear regression if the descriptors are good enough, or one can use neural network regression. And we've, in the last few years, ourselves in my own group have graduated to using neural networks as regression algorithms. But then we then need an application to do the regression on, and that's in the case of the force field, that's typically atomic energies and their derivatives, the forces. But actually, the idea is more general. So you could take any atomic property and you could regress the delta ISO, which is the NMR chemical shift, or the alpha X, which is the polarizability of an atom, is a tensor. And you could make a model of the polarizability as a function of the atomic environment. So what's then, having defined these components, what you do is you create yourself a database of smallish, doable system sizes where the electronic structure can be computed. That gives you points on the potential energy surface, which you then interpolate using the regression that you've chosen. And then you test it. And if it's good enough, you do the science. If not, you go back and you augment your database, you refine the model. When we started this 20 years ago, the big question was how many times you need to go around this loop, and how do you know you need to test every single time? How does this work in practice? It turns out that after 20 years, that this loop is really quite, you don't need to go around many times. It's quite forgiving. Maybe 10 times, maybe 20 times. Nowadays, maybe once already, depending on the application. So this converges reasonably quickly. Just to give you a feeling of what is going on in these high dimensional, in these data-driven fittings, I can't draw high dimension, so I've drawn low dimension. Imagine that I want to fit this dashed curve, and I have data points, which are the red, and I've chosen here Gaussian process regression. There's a lot of choice in these data-driven regression methods, and the answer is going to depend on it. So here in this first row, the only data that I'm allowing to go into the regression are the point values. So what is the value of the function? And the difference between the different panels here is where I take my Gaussian basis center locations. So when you do Gaussian process regression, you can choose where to center your Gaussians, and then you're going to make the function as a linear combination of Gaussians. And you can see that if I take them at the data points, I get one kind of answer. If I take them, the first two here are identical. If I take them on a regular grid, I get a different kind of answer. If I can choose fewer Gaussians and optimize their location, and I'm going to get a different answer. And the blue shading is the uncertainty. Something that we can do with electronic structure theory is not just take function values, but derivatives. So the forces are derivatives of the potential energy, and that's also essentially available at the same time for the same cost as the energies. And here in the second row, I'm doing exactly the same set of fits, but not to the function values, but to the derivatives. And you can see that I'm getting completely different approximations. And sometimes, for example, this one, all the derivatives are really good, but there's an overall shift, away from the function because there's no information on where the absolute value is. And if you use both derivatives and function values, then you see that actually all the fits are much better, and yet still you can get different fits depending on where you choose the data locations. So there's a lot of human learning about how to use these techniques. And linear regression is somewhat simpler than Gaussian process regression, but neural network regression is much more complicated, many more degrees of freedom, many more choices and hyperparameters. Regularization is an absolutely key aspect of all machine learning, all data-driven methods. So we're making assumptions about the smoothness of our data and make choices about how strong those assumptions are, and that influences the fits to a great extent. So here I've drawn a very brief graphical history of the history of ML potentials, so that these ML fits to the potential energy surface. And of course, the origins go back many decades, and even before 2007, people were making low-dimensional fits, particularly to molecules, a few atom molecules. And you could describe, here's the potential energy, it's a cartoon of the potential energy landscape, and you go somewhere to some local minimum, and you take a few data points, and you're approximating that local minimum using one of these regression talks. And then a big breakthrough came in 2007 with Jörg Behler and Michele Parinello's paper, where they've created new descriptors, and that allowed them to make fits in high dimensions, so hundreds of dimensions, and in particular for materials, but also larger molecules too. And the way to imagine that is that there are now many local minima, and you take much more data, hundreds, thousands, tens of thousands of data points, and your regression method is flexible enough. They used neural networks, feed-forward, simple MLPs, but with many, many parameters and well-crafted descriptors of the local environment. And so they could get very high accuracy in the locations, in the local environments, local minima, where they had data. And then myself included, and lots of others have evolved and improved upon these methods in the subsequent 15 years. But just about 2 years ago, again, there was a sort of a leap, I think, which is making models that have very wide transferability, very large generalization. And the way to imagine that is that you fit to just a few data points, relatively few, just in a very narrow part of configuration space compared to everything that you could think of. And that gives you a potential energy landscape that's kind of approximately correct everywhere, very far away from the training data. And that's quite unusual. It was very, very unexpected. And this is what the last 5 minutes of my talk will be about. And people are very surprised. And it's quite unusual, I think, even in the sort of ML and AI world. And what you can, but of course it's not accurate exactly everywhere else. So if you want to make it more accurate somewhere else, because that's where your science is, then you take data there. You can explore it approximately because you have a potential that they can do anything. And then you take new data there, you can refine easily with very little data and get high accuracy wherever you actually did put some data. So we'll come back to the end. But let's go back just to illustrate kind of quantitatively the breakthrough of 2007. And this is actually, the paper is from 2014, so a few years later. But this is the first time that we've seen some being able to solve a task that that really means something from a materials modeling point of view. So we have here tungsten and the errors of empirical potentials on tungsten, elastic constants, vacancy, formation energies, surface energies. And you can see that these three different models, the Born-Order potential, the modified embedded atom method, and the finished Sinclair potential, this sort of derived each 10 years apart, didn't really make much improvement in the overall accuracy with respect to a decent DFT reference. That's not why they were derived. They were derived and created to solve a certain science problem with trends and empirical ideas. So these were excellent methods for what they were describing, but they were not making progress towards actually fitting the potential energy surface. And when we turned on a set of descriptors, and in our case, Gaussian process regression, you just nail all of these things. And sort of arbitrary accuracy. And you want better accuracy, it's not so hard to get. Overall, the milli-EV per atom accuracy that we can get for materials is still true today, and it's actually now limited not by the fitting method, but by the underlying DFT data. So of course, when you do the density functional theory, there are still numerical approximations, and they conspire to have a noise of about a milli-EV per atom. So I have a slide with equations, and I know it's, for most people, learning new equations from a few minutes in slides is in a talk is not the ideal, but I just have them so that to give you a glimpse of how the fitting methods have evolved and how the descriptors evolved over the last 15 years. There's lots of, at least in my own group, and there's lots of analogies. Maybe it gives you a sense of the kind of mathematics that underlies this business. So the smooth overlap of atomic positions, which was sort of used to do the tungsten model that I showed you just now, was made a year earlier. And we start by having a central atom I with neighbors J, and we create an atomic environment density. So this rho I is all the atoms around a central atom I, and we put a little Gaussian on each neighbor. And this rho is then expanded in a basis of YLMs and radial basis functions, Rn, with expansion coefficients. Early on, we used to keep this sigma finite. You'll see later on, it's actually perfectly okay to just have delta functions on each neighbor, same as the sigma equals zero limit. And then you can write the coefficients just as the basis functions evaluated at the neighbor position. And that takes, so these coefficients then are permutationally invariant. It doesn't matter which order you consider the neighbors. In this, sum is a permutationally invariant operation. But we also would like the descriptor to be rotationally invariant. I don't care how an atomic neighborhood is oriented. So it turned out that if you take a square of these C coefficients, C dagger C, normally they're complex, if you choose complex spherical harmonics, and you sum them over M, then you get this power spectrum, which we call P n prime L, so they have three indices for each atom I, and it turns out that that's a rotational invariant, and it contains a rich description of the atomic neighborhood. So it took about 6 years and droughts to realize that this scheme that we concocted up here can be vastly generalized and improved, and he called that the atomic cluster expansion. The paper is from 2019, and I'm switching notation because I'm keeping to the notation of Raf's paper. But basically, but there are close analogies because it's really a generalization of so. So you create this pair basis, which is just the radial R times YLM, and now the R can depend not just on N but also L, The R can depend on the element index if you have different elements, chemical elements in your system, and you sum up the phi's evaluated, the basis functions evaluated at each neighbor, and Ralph called this the atomic basis A, and that's basically displays the role of C in the SOAP formalism. And then in the next step, so C and A are analogous, and then the construction of the rotational invariant is kind of done in two steps. But the first one is the product of the A's with itself, and that's if you just product two A's, so if mu here is 2, then that's exactly the same as what we did in SOAP. But what Ralph realized is that you can actually do this to arbitrary number of A's, and you get a many-body potential, and it's not expensive to do that, or not necessarily expensive, and you get a tensor. And you get this bold A, which is now a many-body representation, and this is now the critical insight, you can simply make that rotational invariant as well. Just as we summed over M here, now we have to sum over L and M, and we get Clebsch-Gordan coefficients. They're more complicated than just know the coefficient 1 here. But when you do that, you get these B bases, which we call the A spaces. It's a complete linearly independent rotational permutational invariant basis for atomic neighborhoods. And so we use the A spaces for a number of applications. I'll show you one in a second. And it's much faster in its latest implementation, in large part due to Christoph Ortner, who's at UBC now. And the ACE, I think in all aspects, kind of supersedes the earlier SOAP representation. And so there is there's more complexity, there are more parameters, but there's higher accuracy. And then the latest, sort of a couple of years ago, what we're using now is a generalization of ACE, and that's called MACE. It's multi-ACE or message passing ACE. We don't really define what the M stands for necessarily uniquely. But what's going on is that we create a phi. Please ignore the C and the H in the first round. I'll come back to that. In the first instance, they are not here. I've just written the general form. But then using those phi's, we sum them up over neighbors here, and then taking a clue from graph neural networks and the deep learning architectures, we have a linear multiplying this tensor, which kind of mixes up the different components, and these are trainable. So this is now no longer a linear model like ACE is, but the tensor product here is exactly analogous. The Clebsch-Gordan product here and the summing over LM is exactly analogous. But as opposed to ACE, we don't stop here, but we have atomic features H, which just start out as the identity, but now we update them using some weighting, linear weights, using the B functions, and we take the updated features and we plug them back in here. So that's why I had the more complicated formula for phi, because we go through this whole process twice. Now with the updated atomic features H, that's why I need a Clebsch-Gordan in the second round, because I need to sum up a product of H and R and Y, and that requires an extra Clebsch-Gordan sum to identify the correct components of the spherical tensor of this product. And then we go through the same summing over the J's, self-producting, and then summing over the Clebsch-Gordan coefficients. And the second round of B's, we just take as the descriptors. And the main person behind all this code and ideas is Ilyas Batatia, graduate student here in Cambridge. So let me show you a few examples. So what we were able to do with ACE is a very large simulation. What's going on here? A large simulation of perovskites. So this is the cesium-lead iodide structure here, which is sort of a frustrated network, a frustrated grid of these octahedra. And because they are frustrated in terms of size, at different temperatures, they do different things. So experimental phase transitions are here and here. This is the vertical axis here are the pseudo-cubic lattice constants. And you can see that at different temperatures, you break the symmetry and get instead of 1 at high temperature, now 2, and then finally 3 different lattice constants in the 3 different directions. And a simple empirical potential really just doesn't get those particularly at all, whereas the ACE model gets the transition temperatures of those phase transitions really quite accurately. There is an offset here of the absolute value of the lattice constant, and that's just simply a well-known DFT error. The DFT approximation underestimates the lattice constants. But once we can train this model, and once we train it typically iteratively, I have a little example here of a movie where this is not exactly the cesium version. This is a hybrid perovskite, but essentially we run MD, wait for it to explode, and then pick those configurations, put them back in a database. And after 16 iterations, and this is the loop that I mentioned at the beginning, you get a stable potential which can run high temperature MD. And once you can do that, you can study something that people want to study about this material. So back to the cesium version, what we see here is 100,000 atoms run for 2 nanoseconds. Completely impossible with electronic structure method. But what the colors show here are the X direction, Y direction, and Z direction tilts of the octahedra, how they relieve their frustration. And what you see here, and what people didn't know before this simulation, is that there are large domains, and in the X, Y, and Z, they don't correlate. So this is a simulation at 500K, so it's one of these intermediate phases, and people didn't know whether that average intermediate phase is that a combination of the lower symmetry phases, or what's the relationship between the different tilts that are possible in this system. And now we know, and people use that in thinking about the rationalizing the observations that you make experimentally of these perovskites. So this was the wrong direction. Okay, so let me show you now, jump a little bit forward, and let me show you a couple of results from MACE. So this is our first attempt at making a transferable organic force field. So this is not materials, but molecules, and we used the SPICE data set that was published quite some number of years ago. It's 1 million molecules calculated with a very high level of DFT. It's omega B97M. It's a hybrid, range-separated hybrid meta-GGA. For those who know it, it contains 10 different elements, lots of different molecules. And we take those molecular energies and forces, fit a MACE model, and then predict properties that people actually want to know. So here are some torsional profiles. You take these molecules that have 2 rings and a single bond between them, and those 2 rings can rotate quite freely. And we can get the potential energy barrier and the full barrier profile for that rotation. And the sort of gold standard coupled cluster here is the black. And what you see here is the level of DFT that SPICE uses is the gray. So that matches the black really quite well. And 3 different MACEs, this blue, green, and red, is the blue, green, and red here. And you can see that the large version of MACE, so with a couple of million parameters scattered around that formula that I put up, sort of gets the torsional profile, within line with accuracy here. And then you take this model and you do much larger simulations. So you can do, one of these polypeptides in vacuum, and they fold up. This is polyalanine. The largest peptide in the database was, a dipeptide. So there is a lot of extrapolation to larger system sizes. And now we can do something that is quantitative, that people actually care about, which is something like solvation. So part of that is hydration of free energy. So what's the free energy difference between an isolated molecule in vacuum at finite temperature and in a box of water? So now we're talking about the simulation of 1,000 atoms. And experiment here is blue. Orange and red are typical empirical models that have been fitted to solvation-free energy. So for small molecules, they basically get it right. They've been parameterized to get it right. But the MACE-OFF gets it right for the right reason, because the potential energy and the forces are quantum mechanically correct. And so this is just a few examples from the first preprint of this paper, but since then we've done dozens and dozens of larger molecules, and this trend continues. And now you can also do more things that the drug industry cares about. So the log P is essentially the free energy difference between water solvation and a fatty, so this is octanol solvation, so a much more aliphatic solvent. And again, experiment here is blue, typical force field is gray, and MACE is green. And so you get the right answer for the right reason. This is a thing that drug companies would want to measure about the proposed drug molecule. So now let me come to the sort of the last 5 minutes. And I promised to talk about the very general ML force fields. And the question is, can we make a force field for all materials? And I didn't think so, but other people did. So credit to Xiuping Ong at UCSD, who have been trying to fit large material databases for many years. And the accuracies kind of improved, but people weren't really using them for anything else other than what Xiuping Ong designed them for, which is to filter proposed crystal structures where in the context of materials discovery. But just very recently, so I guess maybe 18 months ago, we had to, friends of ours fitted our model to the same database that Xiuping Ong used, which is the Materials project. It's about 1.6 million structures. It covers 89 elements. And there is a leaderboard online called MathBench Discovery. And with a little bit of help, the model did very well. Oh, what I'm showing here is just to give you a visual guidance on what's in the training database. So lots and lots of inorganic materials, actually all known inorganic materials. But that's it, just bulk, just very near equilibrium. And so in November 23, our model was at the head of that leaderboard. And this all these columns are very correlated. They're basically how well you describe the energy of a new proposed structure with respect to the convex hull of those elements. And I think around that time, us and other people's successes kind of led to a little bit of a race to see how good can one be. And a few months later, Google released their GNOME model, and it became much better than what our model achieved, but of course on much, much larger data sets. So we fit it to 1.6 million structures. They fit it to 89 million structures that were secret. So nobody knows what GNOME was fitted to. And their model was also much larger, which is all fine, but really the training data scale up was very significant here. And since then, every month there's a new model here. So MatterSim from Microsoft or from Orbital Materials, Equiformer V2 from Facebook, you can see that this is getting saturated. The maximum F1 score possible when you get every energy right is 1.0. So this thing keeps changing all the time. Now, if you introduce a metric that's not just about energies, but forces, so that's the kappa SRME, so that's the root mean square error on thermoconductivity of selected materials, then that requires you to have really good forces. And you see that now you don't correlate. So now things that are not so good not as good as the best one on energies, a MACE model fitted on 12 million structures, actually did the best. This is already very old. So if you check the web page now, you will see even later models doing very well. But this is still in domain testing. What about out of domain? What happens if you take one of these models and you just start doing an MD simulation of your favorite materials problem? So here we tried that, sort of an anecdotal story of why nobody expected this to work. Here's a piece of graphite with an organic electrolyte and lithium salt. In there is a model composition of a battery. And in previous simulations, previous attempts of simulating a system like this, such a simulation would just explode due to the huge variety of structures that you can get. When you simulate it in one of these models that's fitted to the Materials project, you get a stable simulation. You can run this at 500K for a nanosecond, and it just works. And eventually, these lithiums find their way into the graphite, and you get intercalation. So this was completely unexpected and a huge surprise. And then we kind of go crazy, and every student tried this model on their different systems, so not just batteries, but the hybrid perovskites, polymerization of sulfur, amorphous carbon quenching, aqueous interfaces of salty solutions to various solids, hydrogen combustion, catalysis, dichalcogenides, 2D materials, defects in semiconductors. All of this just worked. We couldn't find a system, a real materials modeling problem where you started the simulation in reasonably initial conditions and it just basically did the chemically roughly the right thing. So it didn't explode. Basic chemistry was happening. So the result of that is this paper with nearly 90 authors, not all of whom I know in person. So that was a very interesting experience. It was all written in a matter of 6 weeks. And it's basically a few highlights and then 50 different examples of all the ones that I showed, basically saying what can you get from such a generic model. Some of the highlights that we are particularly intrigued by, this example is MOFs. So we take the foundation model and test it on 20,000 MOFs, none of which are in the training database, and almost all of it, the energy correlation curve is nearly perfect. The ones that are in this cloud here is sort of a numerical discrepancy, the pseudopotential used in DFT. So one of the DFT parameter functions is not the same for those. That was trained, and that gives you an energy offset. But the functionality is perfectly reasonable. So if you take one of these MOFs, MOF 74, and here's a little carbon dioxide molecule, and you compute the free energy of carbon dioxide as a function of space, then you basically get the same answer as you would have got, as people got before, who fitted a machine learning potential to this MOF with lots and lots of DFT calculations specific to this system. And this is not an easy thing. If you take an empirical potential, you get the wrong answer. So now that you have an off-the-shelf model, you can do screening of MOFs. You can take 7 different ions, 14 different ligands, just the example here, and you can do nanoseconds simulations in a matter of days. Here's hydrogen combustion. You start out with hydrogen gas and oxygen gas, you let it go, and you get the right things happening. You get water formation, and this is the different rates of water formation as a function of density and temperature. And when you look at it in detail, you get all the right intermediates forming, and none of this is in the database by itself. You have salts in the database, essentially, as inorganic salts is the closest we get. In the manuscript, we kind of identify for each application what is the closest that you get to those atomic environments in the database. So a word about computational scaling. So this is most of this work is the work of Chuck Witt, who's now at Harvard. And what you should get out of these plots is that it's the number of atoms and it's the throughput in million steps per day, so nanoseconds per day if you're using femtosecond time steps. And these solid curves are, using a single, in this case, a CPU, so one node. And for a very small system, you can get to 10 nanoseconds. And of course, as the system size goes up, you get proportionally lower throughputs. But for 1,000 atoms, you can easily do 2 or 3 nanoseconds. And if you are willing to throw more resources at it, so weak scaling, throw more atoms, throw more CPUs, you get these essentially flat curves. So we can sustain 5 nanoseconds per day essentially forever as you grow your system. And we've done up to millions of atoms. And the similar things happen on the GPU. So GPUs, of course, per flop are much cheaper. You sustain about between 1 and 2 nanoseconds per day, again, reasonably flat. And Chuck is working. There's a few factors in this still more that we could squeeze out, we think. Let me show you some caveats, because there are always some. The materials project, as I said, contains really only near equilibrium structures. So if you highly compress the system, then you get, in our original fits, you basically got nonsense. So this is a number of arsenic structures where if you really, really compress them, you get this as the potential energy curve, which is kind of rubbish, right? When you compress the material, the energy should just go up. And it's not so surprising. This is the data set with this gray histogram, and none of these distances were ever near the data set. So in density, there is very little extrapolation of this earlier method. And really tweaking the model size doesn't really help. What does help is splining into a ZBL reference. So we know that when atoms are super close, less than 1 angstrom, then actually the ZBL potential is a decent approximation. And we also put in the isolated atom reference, as these are the two extremes. And with a few more tweaks, distance transforms on the a transform function on the interatomic distances and normalizing the densities in the intermediate layers of our graph neural network, you can actually get from exactly the same data. Now we get really very reasonable compression curves. With absolutely no data here, we get smooth connection to the splines. So let me see. I'm basically out of time, although we started about 8 minutes late. Let me just show you one slide on fine-tuning, because I mentioned it at the beginning. So what else do we do apart from getting things approximately correct? So this is the normal maze embedding of the atoms into the neighborhood, and then 2 ace layers and the readout. Well, we can split the readouts into 2, and on one of them, we aim to get the original data. And if you have 100 configurations of your favorite new system, we can create a new readout head that gets that correct, but with very little new data. And this is called multi-head fitting, and it works remarkably well. So here's another example from the manuscript that I showed with the 90 authors. So you think about lithium nickel oxide, which is a sort of a prototype battery cathode, and it undergoes Jahn-Teller distortion at high temperatures. So the ab initio molecular dynamics shows you this is the nickel oxygen distance histogram, and at low temperatures you see these 2 peaks very clearly, and they merge at high temperature and a specific temperature. And if this is the original off-the-shelf MACE MP, has the physics of Jahn-Teller in there, but it's not really right. You don't get it at the right temperature, you don't get the right distribution. 100 configurations randomly picked from an MD, from this kind of MD, and fine-tuning, and you get essentially indistinguishable performance from the AMD. So I see a very relevant question in the chat. What would happen if we just did normal fine-tuning, so not multi-head? And what happens then is that you undergo catastrophic forgetting. So basically, for a few epochs, things get better, and essentially you end up completely overfitting your 100 new configurations, and the model is completely unusable and unstable. Of course, if you include tens of thousands of new configurations, then you're essentially making not a universal model, but you're now making a model for that particular material. But the point of the multi-head is that you can get away with very little data as long as you do the fine-tuning in this way. So okay, here's another example which I now don't go through. It's in the archive on catalysis. Let me just say that data matters. So if you do, instead of 1.6 million, you go up to 12 million data points. That's the Alexandria data set. Then many things improve dramatically. So here's the normalized displacement along 111 direction of 3 BCC metals, and this is the stacking fault energy. And you see the DFT is in black, and the original MACE model is in red. And these are very delicate. These are just EVs per angstrom square. And without any fine-tuning, if you take the MACE MPA, and all these models, by the way, are available for download on our website, you get essentially perfect curves without any fine-tuning. Same thing happens for amorphous carbon. So really, this is the closing slide now. And what I promised is that foundation models are systematic derivations, and what we've almost gotten there generally. So our foundation model kind of takes us here in error, so we can do very large systems at the sort of approximate level, but with fine-tuning, with a tiny bit of fine-tuning, we can get down to the ab initio accuracy and have models that are 1 million times faster. Let me skip some of this and just put this slide up with some conclusions, and happy to answer questions.
Thank you. Thank you so much for the wonderful talk. Yeah, Shivanand, he asked the questions, related to the last question.
Yeah, so the fine-tune. So the question, I mean, I'm not quite sure what you're asking. If you do continue learning without the multi-head, the catastrophic forgetting happens. Training more doesn't help. It makes it worse. So I think that this idea of, this is called in the AI business, this is called multi-head fine-tuning with replay. So you're getting some of the old data. The nice thing about it is that you don't need all of the data. So if you're not training one of these models from scratch on the original MP materials project data, it's about 2,000 GPU hours. If you go to the latest data set from Facebook, which is 100 million materials, so that's 100 times bigger, we need 10 times more data. Interestingly, it's about a square root. So, so 20,000 hours, and that's not insignificant. But that's why the multi-head only uses a few % of the original data, randomly picked. And that's enough in typical applications to avoid the catastrophic forgetting. So, yes, Abhijit, you're asking a question about the scaling of the model at high densities. And I think that is absolutely true. So currently, we use a scheme where the cutoff is fixed in angstrom. And there, I've seen some very interesting ideas about changing that. So some people might want to use a certain number of nearest neighbors. One has to be very careful with that, because you have to make sure that the model is still continuous, so that when one nearest neighbor gets replaced by another nearest neighbor that's on the opposite side of the atom, you have to make sure that the model remains continuous. But I think there are tricks for that. I think it might be interesting to rather than doing it by the number of neighbors, to have some kind of cutoff that's adaptive to density. I haven't quite thought that through precisely how that would work, but I think it's certainly true that when you squeeze a material very much, there is a kind of scaling that the Hessian is decays. The interaction decays by the number of atom hops rather than by some absolute scale. So let me just go through some number of questions. So the question is, so the meta-published models using MP and OMAT, and the question is, what about multiple data sets? So that's very interesting. Many people are playing with that. The question really is consistency. So OMAT uses a set of DFT that's really quite close to MP, not quite the same. And so you can use them together. But actually, you might be better off doing a kind of multi-head where, not the fine-tuning multi-head, but where you put the different DFTs on different heads. And certainly, I think one can't just unite data sets that are done with completely incompatible DFTs. I don't think that anyone is really doing that. Next question, are there systematic tests on the anharmonic and non-equilibrium properties? Absolutely so. So the kappa SRME is an anharmonic thermoconductivity. And there are lots of properties that people are interested in that are much more anharmonic than that. So diffusivities, in both solid and the liquid. And, the literature, the recent literature is full of tests like that. And particularly, actually, the people who make MP fits very often, Xu Pingong, the GNOME Google community, lots of other people are interested in not so out of domain universal potentials like I am, but they want to do materials discovery on inorganic crystals, but they're interested in complex properties. So things like lithium diffusivity in a solid state ionic conductor. And there are excellent results on that. Okay, next question. Foundation models perform well on general tasks close to the training set? Well, I don't think so. I mean, I've been trying to show you that they perform well very far from the training set. So I'm not quite sure what you mean. Do you mean foundation models in general in the AI business? Yeah, I think foundation models of the kind that I'm talking about are precisely the opposite. They perform amazingly well, surprisingly well, shockingly well, very far away from the training set.
Yeah.
And we don't know why. So I have to be very honest that we don't really know what aspect of quantum mechanics is being captured here in this architecture, in this GNN message passing architectures that allows this kind of transferability. Why are you getting hydrogen burning chemistry correctly, essentially, when you've seen ice and some inorganic crystals. It's unclear. That's a very, very active research point. What are my thoughts about leveraging foundation models for targeted tasks? So I'm not quite sure what you mean. I think because in these, I think what I've showed you here is that there is this extreme generalization. So maybe you can specify better what you mean. I think you also mentioned distillation. I think there is a role for distillation. These models are much slower than empirical potentials, much slower than an EAM. And one could take these foundation models, generate lots of data, fine-tune them, and then transfer that onto a much simpler model, fit a very fast, very small model onto very large amounts of data. And there's lots of nice papers coming out of that. But Joshua, if you want to, if I misunderstood your question, I apologize. You may want to clarify. Training specialized versus how close you are on the training set. I'm not sure what you meant.
Yeah, Joshua, do you want to unmute and clarify? If Joshua is still there. Yeah. No? It says ions in the in the chat. Okay, so yeah, I do see that the extreme generalizations of your model. But the just to understand the mechanisms, you train on the many different you know, molecular structures and relatively smaller size, right? And
yeah,
then,
almost all of it is less than 50 atoms.
Yeah, and then you learn the force fields, and when you combine them to apply that to the much larger scale, much larger number of molecules and atoms problems, you just use the regressions like the GNN and GP, and you don't impose the physics when you assemble them, when you
No. I mean, look, underneath this, there's a locality decomposition. So quantum mechanics gives you one energy for the entire system and a set of forces, which is the derivative of that one energy, total energy. And these ML models decompose the total energy into atomic contributions. So that decomposition is essential, right? We write the total energy, we approximate the total energy as a sum of local energies. That's what's learned. And that's why these models are extensive. You know, all interatomic potentials do that. Even empirical potentials do that. I didn't emphasize this, but all potentials make that approximation that you divide up the total energy. And that's the learning task.
I see.
Is to learn a local contribution to the total energy that you compute quantum mechanically.
I see.
Maybe Joshua mentions ions. So it's sort of one of the large ones to be computational. How to use the foundation model in large-scale simulation where the large models will be computationally limiting. So I think, you know, if we can do 1,000 atoms for 10 nanoseconds per day, but if you want to do 1,000,000 atoms, and well, if you have the kind of supercomputer access that you guys have, then that would probably work for a nanosecond. But, you know, I accept, of course, that these are 100 times slower than empirical potentials. So I agree that there is a lot of scope in distillation. There's a lot of scope in making a specialized model out of the foundation model with generating lots and lots of training labels using the foundation model or a fine-tuned large model on a specific system, and then you train a small model, which is much faster. And I think that is definitely a viable approach, and I think many people are playing with it.
Okay.
Absolutely.
Awesome.
Yeah, this question about OMOL. So we've already fit OMOL, and we're working with the Facebook team. We have essentially matched their published model on OMOL with a few more tweaks, and we are studying what kind of tweaks are necessary. I think the OMOL data set is super exciting. I was part of the advisory group who helped create that data set. And I think it's it's two orders of magnitude larger approximately than the previous largest than the previous consistent data set, which had that level of electronic structure. And it's much more diverse and much better converged. So I think there's huge excitement in the molecular ML community about it. And we're going to use OML for the next OML 25 for the next couple of years, particularly as we go to charge self-consistent models. So one of the things that I didn't talk about at all is how to bring in electrostatics. Lots of people have done work on that, and we also want to make MACE electrostatically aware, and the OML dataset will be an essential part of this. I just wish that OMAP was as carefully constructed as OML, and I think there is going to be another push in the community to bring up the materials model to the OML kind of standard of rigor. It's hard to go beyond GGA, right? So we will not for a while. We're not going to see imminently 100 million materials computed with a hybrid functional because it's 100 times more expensive than GGA. But in a few years maybe that's possible, and then one can then really think about uniting materials and molecules. So that's a very big outstanding challenge, is that the best functional for molecules doesn't really, or it's too expensive, or doesn't really work for materials or metals, and the other way around. The things that work really well for materials or acceptably well for materials are not really acceptable for high quality molecular work. But I think with extra compute, perhaps we could get a molecular material consistent data set, which of course then opens up hybrid systems, interfacial systems, and that's something that's really exciting.
Okay, I have another question. So I think I heard you're saying that this foundation model is only applicable for the near equilibrium state.
No, it was trained on near equilibrium.
Oh, trained on the near equilibrium.
But it's applicable. Look, I've shown you many examples.
Yeah.
It's applicable everywhere, right? That's the exciting thing, that it does far out of equilibrium stuff, roughly correctly, so that you can explore reaction networks. For example, on the catalysis, the example I didn't have time to show is that you can explore reaction networks because the approximate landscape of troughs and peaks of the molecule potential energy on the surface is approximately right. And then by fine-tuning, you can get the barriers correctly.
Is there a reason why it is limited to, those training data, like the near equilibrium training data?
No, I'm just saying I'm telling you a story. That's what happened. That training data was available. It was near equilibrium. And that's the shocking thing, is that was enough. The OMAT training data, 100 million, is much less close to equilibrium. It includes a lot of MD data. So I think people are making these data sets. There's no reason to have that limitation. I think the real surprise was that it was the diversity that was critical. The diversity of all materials coupled with the MACE architecture and this message passing architecture, it was sufficient to extrapolate from this in some ways very limited training data to any kind of material.
Amazing. Okay.
So Logan is asking about mixed GGA hybrid. People are playing with that. Certainly one option is to fine-tune. So I talked about fine-tuning in the context of going to a certain part of the landscape or for a certain material, but you can easily fine-tune for changing functional, and you can change, you can go to a hybrid for a specific system, and that's not a problem at all. How to do that for a foundation model, right? Can you have a foundation model with the GGA head and a hybrid head? How much hybrid data you need to do that? Very good question. I'm sure people are trying that out. That's an obvious experiment.
Okay. Is there any other questions? If not, let's thank our speaker, Professor Shani, for the wonderful talk and also the discussion, like Q&A sessions. That's awesome. Like, I mean, as you said, it's a mysterious, but it works fantastic. That's awesome.
Okay, thank you very much for listening.
Okay. So that ends the seminar today. Let me stop the